The parts were cold before anything else. Not metaphorically cold, physically cold. The metal beams and brackets inside a proper erector set had the specific temperature of steel that had been sitting in a box in a closet or under a bed or in a garage since the previous Christmas. And when you spread them out across the living room floor on a Saturday afternoon, they held that coldness in your hands for longer than you expected. This is the first thing that separated the erector set from every other toy in the house. It was made of the same material as the world outside. Steel, real. Stamped perforated steel, the same material that bridges were made of, that cranes were made of, that the structural bones of every building you had ever passed were made of. It was not pretending to be those things. It was those things at a scale you could hold. The smell was next. Steel and light machine oil. The faint lubrication applied to prevent corrosion on parts that were meant to move against each other, to fit into gears and ride on axles, and translate one kind of motion into another. The oil was not the cooking oil smell of a kitchen, or the petroleum smell of a gasoline engine. It was mechanical oil, the smell of a machine shop, and it carried with it the suggestion that whatever you were about to build was not a toy in the casual sense of the word. It was an apparatus. Then the sorting, before anything was assembled. The parts had to be sorted. The long perforated girders laid out in order of length. The shorter connector plates grouped by type. The washers separated from the lock nuts. The small brass bushings placed carefully apart from the steel nuts they superficially resemble. The gears into one pile. The pulleys into another. The instructions spread out across the floor next to the parts. Printed on paper that was not glossy. The early instruction books and later manuals had a utilitarian plainness that matched the utilitarian truth of the parts, showing exploded views of completed models with every component numbered and every assembly step numbered in sequence. You picked up the wrench. This too was a specific experience. The wrench in the erector set was a real tool, a miniature tool proportioned for the quarter-inch bolts that held the structure together. But a real wrench, with the weight and hardness of a real wrench. Turning it for the first time was an education in the relationship between torque and friction. Too loose and the joint moved where it shouldn't. Too tight and the bolt stripped the soft brass nut in a way that taught you, immediately and without any lecture, what over-torquing meant and why machinists learned to stop before they reached it. If the feeling of that wrench in your hands is something you still carry, if the sound of a small bolt tightening against a perforated girder is still findable in your memory, take a moment to like this video and subscribe, not for the algorithm. So stories like this don't disappear. The culture that produced the erector set and the childhood that received it deserve to be remembered with the same specificity that the experience itself had. And keeping that record requires people who remember it to say so. The feeling of a joint that was correctly tight was different from any other feeling available to a child's hand. It was the specific resistance of metal against metal. At the point of clamping, the vibration in the wrench stopping as the part seated, the small additional rotation that told you the joint was secure without telling you to go further. This feeling could not be read from a page or learned from a video. It was acquired through practice and through the specific feedback of the bolt that gave too much and the bolt that snapped under too much force. The erector set provided both kinds of education, the success and the failure, in the same session on the same structure in the same afternoon. And it did this without a teacher, without a grade, without any external validation except the structure itself, which either stood or it didn't. The instruction booklets described the numbered models in numbered steps, but the real instruction was in the material. The first time you tightened a girder joint and felt it seat correctly, you had learned something about joint mechanics that no amount of reading about joint mechanics would have given you. The second time you tightened a girder joint, you knew when you were close before the wrench confirmed it. By the 10th time, the knowledge was in your hands. It did not require conscious recall. It was available. Alfred Carlton Gilbert was a man whose biography seems, in retrospect, almost implausibly full. He was born in Salem, Oregon in 1884. He won a gold medal in the pole vault at the 1908 Olympics in London. He put himself through Yale University by working as a professional magician. He graduated with a degree in medicine that he never used, because by the time he completed the degree, he had already founded the Misto Manufacturing Company in New Haven, Connecticut, with his partner John Petrie, and the magic sets that Misto was producing were more interesting to him than medical practice. He was on a train from New Haven to New York City in 1911 when he saw the steel girders. The New York, New Haven, and Hartford Railroad line between the two cities was being converted to electric power, and along the track, the electrification infrastructure was going up. Steel beams erected to carry the power lines, structural steel in its most fundamental form, basic triangulated logic of a bridge or a tower or any other human structure that had to stand against wind and load. Gilbert looked at those girders and thought, what if a child could build that? The idea was not, strictly speaking, without precedent. Frank Hornby, an Englishman working at a Liverpool meat importing business, had patented a construction toy he called Mechanics Made Easy in 1901, which would eventually become Meccano, the British cousin to the American Erector Set, similar in its philosophy but distinct in its parts geometry. Hornby had the same intuition that children could learn the logic of structural engineering and mechanical advantage through physical engagement with real metal parts, and that this learning would be more complete and more durable than anything a classroom could provide. Both men were right. The distinction between the two brands, the Erector Set square girder that could be assembled from 4 perforated flat pieces into a hollow structural member, versus Meccano's angle girder, would become the subject of fierce loyalty among 2 generations of builders on 2 sides of the Atlantic. But the underlying belief was the same. Gilbert's Erector Set debuted in 1913 at the toy fair held at the Broadway Central Hotel in New York City. The full name was a statement of intent: the Erector, structural steel and electromechanical builder. Educational, instructive, and amusing, he sold the toy to retailers and simultaneously launched an advertising campaign in newspapers and magazines that was targeted not only at the children who would play with it, but at the parents who would buy it. Specifically, the argument that America needed engineers and scientists, and that the best time to start building those engineers was childhood. This was a serious argument made seriously, and it worked. By 1915, Erector and the company's magic sets were generating more than $750,000 in annual sales, with a net profit of $100,000. By the mid-1930s, the A.C. Gilbert Company had sold more than 30 million Erector sets in the United States. 30 million. In the decades before the Second World War, before the post-war baby boom, before the suburban expansion and the consumer economy that would multiply the toy market size several times over. 30 million sets distributed through a country where toy manufacturers had not yet developed the national distribution networks that would come later. sold largely through department stores and hardware stores and the early specialty toy shops, each set arriving in a wooden box, or later the distinctive painted steel box, red, green, or blue, and eventually all red, that had the weight and solidity of something meant to last. The physical experience of the Erector set was designed, consciously or not, to replicate at miniature scale the experience of structural construction. The parts were interchangeable. This sounds obvious, but its implications were not trivial. Any bolt in the set could fasten any two perforated parts in this set, because the hole spacing was standardized across every part of every size. This standardization, the insistence that the system's components share a common dimensional language, was itself an engineering lesson delivered through play. A child who built with Erector sets was absorbing without being lectured on the subject. The principle of interchangeable parts that Eli Whitney had demonstrated to the American military in 1798, and that had become the foundational logic of American manufacturing by the time Gilbert rode that train through Connecticut. Frank Hornby had understood this in England more than a decade before Gilbert developed the American version. Hornby had worked out Meccano's dimensional system with mathematical precision, ensuring that every element of the set, the angle girders, the flat strips, the brackets, the wheels, the pulleys, shared hole spacing that was a multiple of ½ inch, so that any part could be connected to any other part at any of several standard offsets. This was not a convenience. It was a philosophy, a system in which complexity emerged not from specialized parts, but from the intelligent combination of simple, universal ones. The engineer's highest achievement in Hornby's conception was not to design a specialized part for a specific purpose, but to solve a structural problem using the most general tools available. Erector and Meccano both embodied this philosophy, and both transmitted it to the children who built with them, in the form not of a stated principle, but of a felt experience of the system's possibilities. The sets grew over time by addition rather than replacement. This was important. A child who had set number 4 could add set number 5's components to what they already owned and expand their building possibilities without discarding anything. The accumulation was additive. This meant that the investment parents made in one set was not wasted when the child outgrew its possibilities. It was enhanced by the next set, incorporated into the larger system. Over years of Christmas gifts and birthday presents and the occasional special purchase for a project that required something the existing set couldn't quite build, a serious Erector set builder accumulated a collection that had real capacity, enough parts to build constructions of genuine scale and complexity, powered by motors that could be geared for different speeds and loads. The instruction booklets that came with the sets were organized around numbered models of increasing complexity. Set number 1 could build certain things. Set number 8, or the deluxe sets that came in the larger boxes, could build considerably more. Cranes that lifted weights, bridges with working drawbridges, Ferris wheels with gondolas that swung as the wheel turned, steam shovels with scooping buckets driven by the included electric motor. The progression was deliberate. You were not expected to begin with the Ferris wheel. You were expected to build the simpler models first. Develop your understanding of how the parts work together, and advance to the complex constructions as your competence advanced. This was curriculum, delivered through steel and nuts and bolts. You learned about gear ratios, not by being told that a small gear driving a large gear reduces RPM and increases torque, but by building a crane and noticing that the motor turned very fast, but the hook lifted very slowly, and by understanding, through the physical sensation of the resistance in the crank, that the speed reduction corresponded to a force multiplication that allowed the crane to lift things the motor alone could not have lifted. This understanding was not stored as a verbal formulation. It was stored as a physical memory, in the hands and in the felt experience of the mechanism. The AC Gilbert Company at its peak employed as many as 5,000 workers in the 5-block complex. It occupied in New Haven, Connecticut, an area that became known as Erector Square, a name that the neighborhood retained long after the factory had closed, rechristening itself as an artist's studio complex, whose industrial bones still bore the proportions of a place where serious manufacturing had once happened. Gilbert opened the Gilbert Hall of Science in New York City in 1941, part museum and part showroom, a physical argument that the boundary between educational and commercial was not where most people thought it was. There was a recurring experience that every person who built seriously with an erector set underwent, and it is worth describing carefully because it was not the experience of success, but the experience of failure. Specifically, the experience of a structure that was nearly complete when it collapsed. The collapse happened for specific diagnosable reasons. A bolt that had been under-tightened finally gave under the torque of a moving part. A joint that had been assumed to be rigid turned out to have a degree of play that, multiplied across the length of the structure, produced a displacement large enough to buckle the whole assembly. Sometimes the motor was the problem. Too much current, too fast to start, a load that exceeded what the gear ratio could handle, and that translated the excess torque into structural failure at the weakest joint. Whatever the cause, the result was the same. A structure that had been minutes from completion was now a pile of parts on the floor, and the work of rebuilding it would begin from whatever state of disassembly the collapse had produced. This experience, the collapse, the diagnosis, the rebuilding, was not a failure of the erector set. It was, in retrospect, one of its most important features, the toy that never failed, that always produced its promised result without requiring the builder to diagnose and correct problems, was a toy that taught very little. The erector set's structural demands were real. The joints had to be correctly tightened. The cantilever spans had to be correctly braced. The gear ratios had to be suited to the load. These were not arbitrary rules. They were the same requirements that governed real bridges and real cranes, reduced to a scale where the consequences of getting them wrong were limited to an afternoon's rebuilding project rather than a structural failure with real-world consequences. The child who rebuilt after the collapse was learning something that no instruction book could have delivered. The specific embodied knowledge of what a joint under load feels like before and after tightening, the physical sense of where the structure's weaknesses are likely to be, the engineering intuition that develops only through direct encounter with the ways that structures fail. Engineers call this knowledge tacit, knowledge that lives in the hands and the senses, rather than in formulas or documents. Knowledge that cannot be fully transferred through description, but must be developed through practice. The erector set was a tacit knowledge delivery system, and the collapse was the lesson that the success couldn't have been. There was a patience specific to rebuilding that was different from the patience required for first assembly. First assembly was patient with the expectation of a result. Rebuilding was patient with the knowledge that the result had already failed once, and that it would require more careful attention this time to succeed, more careful attention to the specific joint that had given way, to the geometry of the bracing, to the sequence of tightening that allowed each part to be set correctly before the next one was added. Child who rebuilt an erector set structure 3 times in a single afternoon had developed, through those 3 iterations, a detailed understanding of why the structure failed that would have taken several lectures to approximate in the classroom. An approximation was the closest a classroom could come, because the physical sense of the failure was not transmittable in words. The pride that followed a successful completion was proportional to the difficulty that had preceded it. This is a general principle of human experience, but the Erector Set made it specific and concrete in a way that very few childhood experiences matched. The crane that had collapsed twice and been rebuilt twice and now stood correctly and lifted the weight it was designed to lift, and did not collapse when you reversed the motor and lowered the weight again. That crane meant something. The achievement embedded in it was genuine. It had cost real effort and real attention and real persistence. The structure knew it in the sense that it stood, and the builder knew it in the sense that they understood every joint and every gear and every structural decision that had been made in the process of building it correctly. The skinned knuckle was the other recurring experience, and it too was not incidental. The small steel parts had edges that were not hazardous in any clinical sense, but were honest about what they were: metal, with the properties of metal, not foam-covered or padded or designed to prevent any contact between material and skin. A wrench that slipped when a bolt unexpectedly gave found the knuckle below it and reminded the hand briefly and specifically that the tool and the material were real. This reminder was not cruel. It was honest. It said, pay attention to where your hand is relative to the tool. This is a lesson that every machinist and every carpenter and every plumber has learned through exactly this mechanism. And the Erector Set delivered it at an age when the lesson could be absorbed without lasting consequence. The post-war decades were the Erector Set's greatest era, and also the era in which the forces that would eventually diminish it were quietly assembling. America in the late 1940s and through the 1950s was a country of extraordinary confidence in its own industrial and engineering capacity, a confidence earned through the Second World War, in which American manufacturing had produced the material for the Allied victory at a pace and scale that had no historical precedent. The country that had built 300,000 aircraft, 86,000 tanks, and 2 million trucks between 1942 and 1945 was not in 1948. Short of confidence about what its engineers could accomplish, this confidence expressed itself in the children's toy market as a valorization of mechanical competence. The child who could build the Erector Set's more complex models, the Ferris wheel with its electric motor and its synchronized gondola movements, the working steam shovel, the automobile with steerable front wheels, was a child who was demonstrating something that the culture around them recognized and valued. The father who had spent the war years working in a defense factory, or flying a bomber, or maintaining aircraft engines, looked at his son's Erector Set crane and saw something real, not a toy, an understanding. Gilbert opened the Gilbert Hall of Science in 1941 and understood that the distinction between play and education was artificial in the context of what he was selling. The men who bought Erector Sets for their children were buying them partly as toys and partly as early professional training, preparing the next generation for a country that would need engineers and scientists in quantities that the existing educational system was not producing fast enough. Gilbert had made this argument to the Council of National Defense in 1918, persuading a room full of cabinet secretaries to allow toy production to continue during the First World War. He brought a satchel full of his educational toys to Washington and let the cabinet secretaries play with them. The Interior Secretary picked up a book on aviation. Gilbert told them, Through the kind of toys American manufacturers are turning out, the boy gets both fun and education. The War Council gave Santa free rein, and the press called Gilbert the man who saved Christmas. The chemistry sets and the microscope sets and the telescope sets that the A.C. Gilbert Company produced alongside the Erector sets reflected the same philosophy, that children could be engaged with real tools at a real level, that the appropriate response to a child's curiosity about the physical world was to give them real materials and real instruments, and a set of instructions that respected their ability to use them carefully. The atomic energy lab that Gilbert introduced in 1950, which included actual uranium-bearing ore samples and a working Geiger counter, perhaps tested the limits of this philosophy, and its $49 price tag, approximately $530 today, was the actual reason it failed to sell, rather than its radiation content. But the spirit behind it was continuous with everything else Gilbert had produced. Real materials, real phenomena, real learning. A.C. Gilbert died on January 24th, 1961. He was 76 years old, and he had spent 50 years building a company whose products had passed through the hands of more than 30 million American children. The loss of his specific vision, his direct, physical, non-theoretical commitment to toys that treated children as capable of engaging with real materials, proved more consequential than the company's ownership change suggested it would be. His son, A.S. Gilbert Jr. took over the company, but the specific gravity that the founder had given to the enterprise was not transferable. Gilbert had built more than a toy company. He had built an argument, made in physical form. The argument that children's play and adult engineering were not separated by a developmental boundary that required years of formal instruction to cross. The Erector Set was the proof of this argument. A child's toy that produced genuine engineering understanding through genuine engineering engagement. The argument was correct. The evidence for it sat in the careers of the engineers and machinists and mechanics and surgeons and architects who had built erector sets in their childhoods and who carried the tacit knowledge of those builds into their professional lives. Arguments require advocates, and Gilbert had been the advocate with the most credibility and the most commitment. And when he died, the argument lost its most effective voice at exactly the moment when the commercial pressures against it were beginning to intensify. The Gilbert Hall of Science on Fifth Avenue in New York City had been his physical version of the argument, a space where children could encounter real science and real engineering in forms that engaged rather than intimidated them, where the boundary between educational exhibit and commercial showroom was deliberately blurred because Gilbert had never accepted the premise that the educational and the commercial were in tension. You could learn something real from a toy that cost money. The learning was not diminished by the commerce. The Hall of Science operated from 1941 through the early 1960s and drew hundreds of thousands of visitors, not because it was free or because it was mandated by some civic authority, but because the content was genuinely interesting to children who encountered it, and interesting things draw children without the application of force. The Jack Rather Group acquired the company's remaining shares after Gilbert's death, and the company went bankrupt in 1967. The Gabriel Company of Lancaster, Pennsylvania, purchased the Erector brand and continued to market it. But the trajectory of the changes that Gabriel and subsequent owners made told the story of what the market was asking for: plastic parts, simplified assembly, fewer components, lower price point. These were rational commercial responses to a market that was moving away from complexity and toward convenience. They were also, one by one, the elimination of the specific features that had made the Erector Set what it was. The cold steel, the real tool, the bolt that stripped if you over-tightened it, the joint that failed if you didn't tighten it enough. Ideal Toys acquired the trademark in the 1980s, followed by Tyco Toys, followed by Meccano SA of France in 1990, which finally unified the two great traditions of metal construction toy under one corporate roof. The product that emerged from this lineage continues to be sold. Meccano in Europe, Erector by Meccano in the United States, and it retains some of the steel parts that define the original. It exists in a toy market that has been transformed in ways that Gilbert could not have anticipated, and that the Erector Set in its original form was not designed to survive. The plastic toy arrived in the post-war decades at first as a supplement, and then as a replacement. Plastic was lighter, cheaper to manufacture, more color capable, and could be molded to any shape the designer specified without the constraints of die-stamped sheet metal. The injection molded toy of the late 1950s and 1960s offered things that steel construction toys could not: bright primary colors, enclosed shapes, surfaces that could replicate the appearance of real objects more faithfully than steel beams and perforated plates. The Erector Set could build the functional logic of a crane. A plastic toy could look exactly like a crane while you held it in your hands. The functional and the representational were different satisfactions, and the market was discovering which one was more commercially reliable. The liability culture that developed through the 1980s added its own pressure. The skinned knuckle and the stripped bolt and the sharp metal edge, the honesty of real steel parts, became an illegal and commercial environment that was increasingly focused on minimizing any possible harm to any possible child. Liabilities rather than educational features. The wrench that might slip, the bolt that might be swallowed, the gear mechanism that might catch a small finger. These risks had always existed and had always been managed through the instruction books that came with the sets, through parental supervision, through the child's own developing understanding of what to be careful about. In a culture that was beginning to require the elimination of the risk rather than the management of it, the Erector Set's honesty about its own physical reality became commercially disadvantageous. The digital entertainment revolution arrived in the same period and offered something that the Erector Set could not: feedback at digital speed. The video game's response to your input was immediate, unambiguous, and consequence-free in any physical sense. You pressed the button and the character moved. The relationship between input and output was clean and total. The Erector Set's relationship between input and output was mediated by physics, by the imperfect fit of parts, by the resistance of real materials, by the consequences of insufficient attention to the structural logic of what you were building. This mediation was educational. It was also slower and more frustrating and required more persistence than most modern entertainments required. The question that the Erector Set story ultimately poses is not about toys or markets, or corporate ownership, or the liability culture of the late 20th century. Those are the mechanisms of the story, not its meaning. The question is about what kind of competence a culture produces in its children, and what happens when the specific training ground for a specific kind of competence disappears. And behind that question, another: whether the people making decisions about what children should engage with have fully understood what the steel and bolt construction toy was actually providing, or whether they saw only a market category declining and not the specific educational content that was leaving with it. The engineer who designed a highway interchange, the machinist who held tolerances of 1,000th of an inch, the surgeon who operated through a mechanism of small, precise movements, the architect who understood why a cantilever worked and where it was likely to fail. These people developed their fundamental mechanical intuitions somewhere in their formative years through engagement with physical systems that had real properties and real constraints. For a significant portion of the engineering and technical generation that built the infrastructure of mid-20th century America, that engagement happened at least partly through the Erector Set, or through Meccano, or through the other mechanical construction toys of the era. Through the real steel and the real bolts and the real failure that preceded the real understanding. What replaces this engagement? Digital tools, without question, develop their own kinds of spatial reasoning and their own kinds of problem-solving competence. The child who grows up with sophisticated software, design tools, simulation environments, coding languages that make things happen, is not intellectually impoverished. They are differently equipped. The question is whether the specific things that the mechanical engagement provided, the felt understanding of load and stress, the physical memory of what a well-made joint feels like versus a poorly made one, the experiential knowledge of the difference between a mechanism that works and one that is about to fail, are being developed somewhere in the curriculum of contemporary childhood, or whether they have been quietly eliminated as the curriculum evolved toward the screen. The bolt-tightening knowledge lives in the hands, not in the head. The understanding of gear ratios that is developed through physical play with real gears is stored differently, more deeply, more accessibly in context where it is needed, than the understanding of gear ratios that is transmitted through a formula in a textbook. The failure of the Erector Set structure produces a form of understanding that the non-failure of the digital simulation does not produce. These distinctions may seem small. In aggregate, across a generation of children who did not encounter real mechanical systems in play, they are not small. If you learned something real from tightening a bolt that's stripped, from rebuilding a crane after it collapsed, from the skinned knuckle that reminded you to keep your hand away from the wrench path, leave that memory in the comments, not as nostalgia for its own sake, but as evidence. The record of what these toys actually gave to the people who used them seriously is not preserved in any institution's archive. It lives in the memory of the people who remember it, and the only way it reaches the people who need to hear it is if the people who remember it choose to say so. This channel exists partly for that reason, to keep the record of what mechanical learning felt like and what it produced, before the last people who know firsthand have moved past the age of remembering. Return to the floor. The afternoon light has moved since the sorting began, and the shadows of the girder piles have shifted on the carpet, or the hardwood, or the linoleum, depending on which floor this particular memory belongs to. The parts are spread across it in the careful disorder of someone who was sorting before they began to build. The long girders are in a row, shortest to longest. The corner brackets are in a pile that is not quite orderly. The small brass nuts are in a separate pile from the steel bolts, because they look similar enough at a glance that confusing them costs time, and time spent searching is time not spent building. The instruction book is open to the page, showing the model you have decided to attempt. The third one in the sequence, because you completed the first and the second, and each time you completed one, you understood the next one slightly better before you started it. The wrench is in your right hand. The first bolt and the first nut and the first two pieces of perforated steel are in your left. You are about to begin the thing that will take the afternoon, and possibly the evening, and possibly part of the following morning when you return to it and notice that the joint you thought was tight has worked slightly loose in the night, you're about to learn something. You do not know yet what it is. The structure you're going to build doesn't know yet either. The bolt is cold. The metal is cold. That is where it starts.